Okay, so in this video, we want to review the derivative of a function, and especially looking at functions that are not necessarily functions of x, but functions of other variables. So suppose that, and we'll look at a few examples of functions that are maybe functions of x, functions of y, functions of str, and so on. So suppose that y is the function, say, x to the 4 minus 3x plus 1. Well, here y is a function of x, so of course we'd find the derivative of y with respect to x. So it's dy over dx, and that would be simply 4x cubed minus 3. What if we had now y was t to the 4 minus 3t plus 1? Now y is a function of t, so if you differentiate y, you would differentiate y no longer with respect to x, but with respect to t. So it's dy over dt. And of course, the fact that we change the variable changes nothing. We still apply the same rules of differentiation. So we'll get 4t cubed minus 3. So let's do a few other examples where we'll change the variable. And of course, we have to differentiate the function with respect to whatever variable the function is a function of that variable. So what if we had, say, y is equal to cosine of e to the 2t? Well, here y is a function of t, so we differentiate y with respect to t. The derivative of cosine is negative sine. Negative sine of what? Of the argument, e to the 2t. But there is still e to the 2t left over. By the chain rule, we have to multiply what we have so far by the derivative of what's left over. This is an exponential function base e. Differentiate that. The derivative of the exponential function base e is itself, e to the 2t. There's a 2t left over times the derivative of 2t with respect to t. That's just equal to 2. And of course, now you write the simpler terms first. You'd have negative 2 e to the 2t sine of e to the 2t. And I will leave that up to you. But you see, whether you have a function of x, a function of t, it doesn't matter. You differentiate with respect to the appropriate variable. What if y, say, was a function of z? What if y was the ln of z cubed plus 6z squared plus 4? Now, if you differentiate this function, y is a function of z. So you have to differentiate, you have to differentiate y with respect to z, so dy over dz. Well, the outside function here is ln. The derivative of ln is 1 over whatever the argument is, z cubed plus 6z squared plus 4, times the derivative of what's left over, and we differentiate this with respect to z. So we'll get 3z squared plus 12z plus the derivative of 4 is 0. And now we have the derivative of y with respect to z. Of course, this looks rather silly. Put this on top and factor your 3z, and you'll get 3z times z plus 4 divided by the cubic, z cubed, plus 6z squared plus 4. So if we change the variable, it doesn't change anything other than we differentiate with respect to the given variable. Let's do a couple more examples. What if we had y was a function of u? So say y is equal to u squared times the tangent of, say, 3u. Well, here now y is a function of u, so we differentiate y with respect to u, so dy over du, and we're good to go. Of course, here we have a product between u squared and tangent of 3u, so we must use the product rule. So the derivative of the first function with respect to u, well, the derivative of u squared with respect to u is just 2u, times the second function, tangent of 3u, plus the first function, u squared, times the derivative of tangent of 3u with respect to u. We have here a composition, so we use the chain rule. The derivative of tangent is secant squared. Of what? Of the argument, 3u. But there's a 3u left over, so by the chain rule, we have to multiply what we have so far by the derivative of what's left over. The derivative of 3u with respect to u is just 3. In the end, there's not much we can do other than factoring a u from both terms, and we'll get u times, well, 2 tangent of 3u plus 3u secant squared of 3u. And that's it. Let's do one last example. What if our function y is a function, say, of v? Let's go with v cubed minus 1 over 2v plus 3. Now here y is a function of v, so if we differentiate y, we will differentiate y with respect to the variable v. Here we have a quotient of two polynomials, so we use the quotient rule, which will be the derivative of the numerator with respect to v, that's just 3v squared minus 0, so it's 3v squared, times the denominator, 2v plus 3, minus the numerator, v cubed minus 1, times the derivative of the denominator, which is simply, again, with respect to v, is simply 2, over the denominator all squared, so 2v plus 3 squared. We can look on the numerator. We have a difference of two terms. As always, we look for common factors, and there are none. So now we just multiply and regroup similar powers of v. So what will we get? Well, 3v squared times 2v will give us 6v cubed, plus 3v squared times 3 plus 9v squared, minus twice of this, so minus 2v cubed plus 2 over 2v plus 3 squared, regroup these two terms together. It's not much of a simplification, but 6v cubed minus 2v cubed is 4v cubed, plus 9v squared plus 2 divided by 2v plus 3 all squared. So you see, whether you have a function of, so if you have a function of x, differentiate with respect to x. Function of t, differentiate with respect to t. Function of z, differentiate with respect to z. Function of u, differentiate with respect to u. Function of v, differentiate with respect to v. And you see, it makes no difference whether you have a function of x, t, z, u, v, or any other variable. If you have a function of a given variable, when you differentiate with respect to this variable. And why am I reviewing this? This will be for our next topic, which will be related rates. And we'll very often have functions of t because we'll have variables that will be changing as a function of time. So very often our functions will be functions of t. Now, one last comment, which is something we have seen before, but if y, say, is a function of t, and suppose that y is a function of t, which represents the position of an object in space. If you have an object moving in space in a linear fashion, so in a straight line, so a linear motion, recall that the velocity of the object is just the derivative of the function with respect to t, right? So recall these synonyms. The slope of the tangent line if you think of the function, suppose it looks something like this. You have the position of an object moving in a linear fashion as a function of time. So as time goes on, the position changes. So if this is your point t, you have the tangent line at that point. And recall that the slope of the tangent line is what we define to be the derivative of the function at t. But the derivative is just dy over dt, right? It is the change in y over the change in time. And so we can also look at this as a rate of change, right? A rate means a fraction, and the derivative is a rate of change. It is the change in y over the change in time, which is why it is the slope of the tangent line. So the derivative is a rate of change. But we also know, and this is true for any given function of t, but we also know that if f of t represents the position of an object moving in a linear fashion, the derivative is also the velocity of the object. So the slope of the tangent line to a function is what we call the derivative. If y is a function of t, it is dy over dt. That is the rate of change of y with respect to t, and that is the velocity of the object. And you will see the topic of our next chapter is related rates. Rate of change, therefore velocity. We'll look at objects moving in space with respect to one another, and we'll have to relate them, and then we'll differentiate with respect to time to find the velocity of the different variables. So always keep this in mind. The derivative is just the slope of the tangent line, which is the rate of change of the dependent variable over the independent variable. And if we have a function of t where t represents time, and the function gives the position of an object moving in a straight line, the derivative is the rate of change, which is the same as the velocity of the object. Of course, the instantaneous velocity of the object. It is the velocity exactly at time t, and that's what the derivative is. And one last observation, this is something we know, but if the derivative is positive, the slope of the tangent line is positive, therefore the function is increasing. If the derivative were negative, that means that the slope of the tangent line would be negative, and the function would be decreasing. So keep this in mind. If you have a variable and the derivative is positive, positive slope means the variable is increasing. If you have a variable with negative derivative, the rate of change is negative, the derivative is negative, therefore the function is decreasing. And this goes both ways. If you have a function of time that is increasing, its derivative will have to be positive. If you have a function of time that is decreasing, the derivative is negative. And with this, we're good to go for our next topic, which, as we've said before, will be called related rates.